So in this video, we are going to see about the mechanical properties of the materials. The important properties like strength, stiffness, toughness, brittleness, elasticity, plasticity, malleability, ductility, resilience, fatigue limit, creep and hardness are discussed in the video part 1. In part 2 video, we will be seeing about the stress strain curve obtained as a result of tensile test from the mild steel specimen. So coming to the mechanical properties, the important properties are strength. It is commonly called as tensile strength, stiffness, a measure of flexural strength, toughness, a measure of impact strength, then elasticity, plasticity, malleability, ductility, brittleness, fatigue limit or endurance limit, hardness, resilience and creep. So how the mechanical properties are evaluated? So before going to that, we want to see about the types of materials. So types of materials according to the physical properties, they are classified as elastic material, plastic material, malleable material, ductile material and brittle material. So based on the stress strain curve, we can obtain the material strength, stiffness, elasticity, plasticity, ductility, brittleness and toughness for different materials like ceramics, metals and polymers. So coming to the elasticity, we know that elasticity is the ability of the material to deform under the load and regain its original shape when the load is removed. So consider a body, when the load is applied, the body deforms, it changes its shape and size. Once the load is removed, the body comes back to the original position. So the property of restoring it to the original position is called elasticity, and all the materials, mostly all the materials are elastic up to the elastic limit or the yield point, and plastic deformation will be occurs after the elastic limit. So in the stress strain curve, you'll be having the elastic limit or yield point level. So up to this level, the shaded level in the blue color. So the body behaves in the elastic. After that, the plastic region continues. So coming to the plasticity, it is the ability of the material to deform under the load and do not regain its original shape when the load is removed. The ability to easily get deformed, that is shaped or molded permanently without any failure. Take the same example, I am applying the load, the body deforms. When the load is removed, the deformation is permanent. So it is a plastic form of, it reflects the plasticity of the material. So coming to the malleability, it is the ability of the material to deform into thin sheet under the action of forces. So we are taking a metal block and applying the forces. What happens? The body deforms and forms into a thin sheet. So the property of the material to deform into thin sheet is called malleability. The best example is material gold, aluminium, copper, tin, lead and steel. All are malleable. While applying the force, the body deforms and gets into a thin sheet. Ductility is the ability of the material to drawn into thin wire under the action of tensile forces. So ductility is the property used in wire drawing. It is an elongation is the measure of ductility. So you can bend the ductile material, but the brittle material will be broken. Brittleness is the ability of the material to break without any significant deformation under the action of forces. So elastic body, elastic material or a ductile material will show any significant deformation before the failure. But the brittle material will not show any indication of failure. It shows sudden failure. So from the stress strain curve, we can tell the brittle material and we can identify the ductile material. So the ductile material follows the point from A to B dash. Brittle material follows the curve A to B. So the brittle material fractures at the highest stress compared to the ductile material. So brittle material is toughness is less, but the ductile material has a higher toughness. So coming to this curve, based on the strength and the toughness, so when the toughness is high, we can tell it is a tough material. When toughness is very less, we can tell it is a brittle material. Similarly, when the strength is less, we can tell it is a weak material, and strength is high, we can tell it is a strong material. So this graph represents the variation of toughness and strength of the different materials like wood, plastic, glasses, ceramics, composites, metals and alloys, foams. So here the higher in the x-axis will be getting the tougher material. Higher in the y-axis will be getting the stronger material. So as an outline, we can define the elastic material as it is the ability to deform and regain its original shape when the load is removed. And plasticity is defined as it is the ability to deform and do not regain its original shape when the load is removed. Malleability is defined as the ability to deform into thin sheets under the tensile forces. Ductility is defined as the ability to drawn into thin wire under tensile forces. Brittleness is defined as the ability to break without any significant deformation. So coming to the elastic mechanical properties, we are having 12 mechanical properties we'll be discussing, like the properties like strength, stiffness, toughness, brittleness, elasticity, plasticity, malleability, ductility, resilience, right? All these properties can be measured or can be noted with the help of the stress strain curve. So coming to the importance of the mechanical property, we can see the aircraft, the 5 aircrafts are here. So I'm starting from the bottom. So when the wing is bending or it is bending downwards, it is due to the weight, heavy weight. So what happens when the weight is very high, the wings are bending towards downwards. So that indicates density is higher. So we want to select a material with the lowest density. Coming to the next thing, the material, the wing is broken here. So it is not having the toughness. So we want to increase the KIC factor, that is fracture toughness is the ability of the material to absorb the shock loads. When there is a shock load, wing may fail. Similarly, the third condition, we can see the wing is having the permanent plastic deformation. So that indicates the lesser yield strength. So the yield strength should be higher for a material, so to withstand the permanent deformation. Similarly, in the first case, the wings are bending in the upward direction. It indicates the stiffness is less. So that it needs more Young's modulus. So Young's modulus will be having is the measure of stiffness of the structure. In the first case, we can tell the wings are perfect, right? So it indicates the material is stiff, it is strong, it is tough enough, and it is light. So for a design engineer, it is essential to consider all these properties like density, fracture toughness, yield strength, and Young's modulus. So coming to the testing for getting the mechanical properties, there are different main mechanical properties like strength, stiffness, hardness, and toughness. Strength can be measured with the help of tensile test, compression test, shear test, and flexural test. Stiffness can be measured with the help of slope from the stress strain curve. For hardness, we have 4 tests, that is Rockwell test, Brenner hardness test, Vickers hardness test, and Shore hardness test. Coming to the toughness, toughness can be measured with the help of universal testing machine using the stress strain curve, and it also measured with the help of a impact test. There are 2 types of impact test, ISOD impact test and Charpy test. So stress is the quantity that describes the distribution of internal forces within the body. Stress is the force acting per unit area. So stress can write sigma is equal to force by area. The unit is Newton per meter square or Pascal. Strain. Strain is the quantity that describes the deformation that occurs within a body as a result of stress. We can describe the strain epsilon as change in dimension by original dimension. So that is longitudinal dimension, we can take it as length. Lateral dimension, it can be taken as diameter for the cylindrical specimen, and breadth and thickness for the rectangular specimen. So here we can describe the Poisson's ratio, mu is equal to 1 by m, that is the ratio of lateral strain to the longitudinal strain. So coming to the strength, it is the ability of the material to withstand the load without any failure. So consider a tensile test. I am stretching the rod. What happens? The length is elongating. At the same time, the diameter is reducing. At one point, the neck is formed and the fracture happens. So it is represented as stress strain diagram starting from the point origin to finally to the fracture. So at the maximum level, that is the ultimate tensile strength, the necking occurs. That is the change in dimension suddenly occurs, the neck forms. So once the neck forms, it is an indication that the body is about to fail. So neck is formed in the ductile specimen. So here you can describe the strength as force by area. So both stress and strength are equal. So tensile strength, that is ultimate tensile strength, is defined as the stress at which the material fails due to the tension, compression, shear, bending and torsion. The force per unit area required to break a material is called ultimate tensile strength. So in this graph, you are seeing the high strength material is stronger. The weak strength material, we can represent it as weak material. So in the factor of 0.1 to 10,000. So highest strength is ceramic material, followed by porous ceramics, followed by glasses, followed by metals and alloys, and followed by wood and wood products. So composite stands between 50 to 1600 megapascal, and polymer stands between 5 to 80 megapascal, and rubber stands between 2 to 30 megapascal. Polymer foams are weak by their nature. So coming to the mechanism of failure in the ductile material. So once the neck is formed, after that we will be continuously giving the force. What happens? The crack is initiated, and after that the crack grows perpendicularly to the applied stress. Then crack is initiated, propagated, then finally the fracture is occurred. So the mechanism of failure in the ductile material is cup and cone fracture. Yield strength. So coming to the stress strain curve, so yield strength is above the elastic limit, that is upper yield point, and the lower yield point. So it is a point where the stress causes the sudden deformation without any increase in the force. It is called yield limit. After this yield point, the deformation is permanent. That is coming to this, it's a plastic deformation. The highest stress, that is nothing but upper yield before the sudden deformation. Then the lower stress value, that is the lower yield, represented by YL. So for most of the materials, the point P and E will be equal. That is nothing but sigma E is equal to sigma P. Yield level is equal to elastic point. So this yield strength represents the highest stress of a structure that can withstand before the plastic deformation. So this shows the stress strain curve. The y-axis you have the stress, in x-axis you have the strain. So up to this proportional limit, the body behaves in the elastic nature. After that, you have the proportionality limit, then upper yield point, then lower yield point, then the curve is traced up to the maximum ultimate tensile stress, and finally to the fracture point. So beyond this, the material gets failed. Working stress or factor of safety. So this factor of safety is very important in designing a material for any structures, right? The stress is capable of preventing the failure is called working stress or allowable stress. Once the safety is enhanced, we can reduce the risk. So it is the role for the any engineer to provide a suitable margin against failure. So this factor of safety is an important term considered in a design point of view, where it is the considering the ultimate tensile strength and working strength for a ductile material and yield strength for a brittle material. So this is the curve which shows the strength of the different materials. Suppose I want to select a material for certain applications. I need for 300 megapascal, right? So for 300 megapascal, I want to select material which is coming around 1000. So it is nearly 3 times of the uh, working stress. So the material, I can enhance the safety by 3 times. Like that, we can select the material based on the material selection chart. So coming to the stiffness, it is the ability of the material to resist deflection under the action of forces. Stiffness is inversely proportional to deflection. If stiffness is more, deflection is less. So Young's modulus represents the stiffness of the material. So from the stress strain curve, up to the slope up to the elastic limit, you can measure the slope, you can get the Young's modulus. Once the Young's modulus value is very high, stiffness is very high. So from the stress strain curve, we can classify whether the material is flexible and weak, whether the material is flexible and strong, whether the material is stiff and weak, whether the material is stiff and strong, according to the slope of the stress strain curve. So from this chart, we can see the Young's modulus, lesser Young's modulus, we can tell it is a flexible material. Higher Young's modulus, we can tell it is a stiffer material. Similarly, light density material, you can call it as lightweight material. And heavy density material, you can call it as a heavy material. So mostly the metals and ceramics falls under the heavy category. Composites and porous ceramics forms under the medium density category, and polymers and rubbers, some rubbers, and mostly the foams and wooden products comes under the lightweight category. So coming to the Young's modulus, ceramics and metals have the more Young's modulus, and certain composites also have the more Young's modulus. Especially carbon epoxy composites, the modulus, Young's modulus is very high, and it finds the applications in the frames of the bicycles. Coming to this next graph, it shows the variation of specific strength with respect to specific stiffness. Specific strength is nothing but strength to weight ratio. If the strength to weight ratio is very less, we cannot employ the material for carrying the high strength. Similarly, the strength to weight ratio is very good. The material have more strength, at the same time the weight is also very high. Similarly, the stiffness, good stiffness to weight ratio. Mostly the metals and ceramics have the stiffness to weight ratio. Coming to toughness is also called as impact resistance. It is an ability of the material to resist breaking under the action of shock or impact loads. So the toughness is the combination of strength and ductility. So larger the area, tougher is the material. So this larger area means larger area in the stress strain curve. We can tell the material is tough. That is nothing but the ductile material has the most area, stretches the most area in the stress strain curve. So we can tell the ductile material is tougher. So in this curve, you can see it is a stress strain curve of a brittle material and ductile material. So the ductile material has the more area. So it forms the combination of strength and toughness, but the brittle material is very less tough. So coming to the fatigue, it is the failure which involves the cracking of machine components due to cyclic or fluctuating stress, which is caused due to vibrations. So fatigue strength or endurance limit and fatigue life are the terms used to describe the fatigue behavior. So this fatigue behavior is studied using the SN curve. So S stands for stress and N stands for number of cycles. This curve shows the relationship between logarithmic cyclic stress amplitude S and logarithmic number of cycles of failure represented by N. So fatigue lowers the mechanical properties due to the cyclic loading. Once the material is subjected to cyclic loading, automatically the strength and stiffness gets reduced. So it is the highest stress that a material can withstand for a given number of cycles without breaking. So fatigue is a form of a failure of a machine component due to cyclic or fluctuating stresses causing as a result of vibration. So fatigue occurs in the material subjected to continuous stress leading to fracture or failure. So from the SN curve, we can get the relationship between cyclic stress amplitude and number of cycles to the failure. So the cyclic loading occurs in the landing of planes, vibrating of plates, bridges, bearings and gears. Resilience. Resilience is the ability to absorb the energy when it is deformed elastically and up to its yield point and to recover it once the load is removed. So it is the measure of by the amount of energy absorbed per unit volume within the elastic limit. So from the stress strain curve, mark a point up to the yield point, that is yield stress. From the yield stress, project a vertical line, it represents the yield strain. So it forms a triangle. So this area of the triangle is represented by the resilience UR, that is half BH, half into sigma y into epsilon y. So resilience should be considered when the material is subjected to shock loading. Brass and rubber has high resilience modulus compared to ceramics and cast iron. So coming to the creep, it is the tendency of the material to deform permanently under the influence of continuous mechanical stress. Creep is defined as a time-dependent deformation subjected to continuous stress at elevated temperature. Under normal conditions, the designs are based on the yield stress or ultimate tensile stress. But in high temperature environment, the material is failed due to its low stress over a long period of time. So mostly this creep occurs at high temperature, there is nothing but thermal creep, and it also occurs at room temperature for material like lead. So this is the setup for measuring the creep testing. The test piece is similar to that of the test sample as we use in the tensile test, and it is enclosed inside fitted inside the furnace, applied with the load mechanism. So here you have the wire. Once due to heavy load and the continuous thermal stress, what happens? The wire is stretched. So the measurement of stretching is measured with the help of the telescope to identify how much the material gets displaced. So this purpose of the creep test is to record the strain over a period of time at a certain stress and certain temperature, so that this data can be used to make a material selection at high temperature applications. So this is a creep curve. Initially it is plotted between the strain and the time. So initially there will be some deformation due to the load applied. After, due to load and thermal stress, initially the primary creep region is formed at a rapid rate. The length is increased up to the point A to B, which forms the primary creep region. So during this point, the material is work hardened. After that, from B to point C, it is termed as secondary creep region, where we can expect a constant creep rate up to C. From C to D, we can tell it as a tertiary creep region. The cross-sectional area is reduced and grain size is changed and voids are formed, neck is formed, and finally the fracture point D is noted. So this is a chart represents the strength and the service temperature. So mostly all the materials will behave good at room temperature, but when the temperature goes high, the material behaves in a different manner. So we want to check the application temperature and the employ a suitable material for that particular applications. For that, we need to have a good idea about the behavior of the material at certain temperature, high temperature like 400, 500, 800 degrees centigrade and beyond 1000, right? So mostly metals will have a good strength maintenance. Maintaining the strength of the metals and alloys will be good. Ceramics also very good. So then coming to the composites, up to the maximum temperature of around 300 to 325 degrees centigrade. So we cannot employ a composites beyond 300 degrees centigrade. Similarly, we cannot employ the rubber beyond 300 degrees centigrade. We cannot employ the polymers up to 300 degrees centigrade. Similarly, wood, that operating temperature itself, it is less than 200. So the properties get changed and we cannot experience a good performance of the particular material. So these are some of the examples of the creep. Mostly the flat spotted on the tire of the civil caster. So once the civil caster carries the load for a long time, what happens at the stationary load? This flat spot is formed, and coming to the steel bolts, after no usage, it gets loosened after a certain time. And the good example is PVC hose rolled up for a long time, maintain its circular shape when it is unrolled. So these are some other examples. Wooden creep in the roof structure, creep in our bookshelves due to continuous loading, and also absorbing of moisture, right? Our bookshelf gets sagged. Similarly, tuning of guitar forms the best example of creep in wood. So coming to the hardness, it is the measure of resistance to localized plastic deformation induced by mechanical indentation. So hardness is defined as resistance to penetration by metallurgist, resistance to scratching by mineralogist, and resistance to machining by machinists. Hardness value can be correlated to tensile strength of metals and alloys. So it is an indicator of other properties like machinability, wear resistance, toughness, and ductility. So once you apply the indentation or scratch, the softer material forms the more indentation compared to the harder material. And one more thing, the hardness is correlated with the wear resistance. More harder material wears less and a softer material wears more. So there is a correlation between hardness and wear resistance. So this is the mechanism of hardness measurement. You'll be having the load, you have the timing mechanism, you have the diamond pyramid indenter or steel ball indenter according to the different types of hardness test. The load is applied due to the fulcrum, the penetration of the indenter happens on the specimen. Based on the depth of penetration and size of the penetration, we'll be determining the hardness. So there are different types of hardness test like Binel hardness test, Rockwell hardness test, Wicker hardness test, Shore hardness test, Moe hardness test, and Knoop's hardness test. So applications of hardness test. Once you know the hardness of the material, we can use the data to research in heat treatment and to do surface hardening characteristics. You can do R&D, inspection, testing. So hardness can be correlated with strength, ductility, wear resistance. Once the hardness is high, have the high strength and also have the high wear resistance. So in this video, you have seen about the different properties like strength, stiffness, toughness, brittleness, elasticity, plasticity, malleability, ductility, resilience, fatigue, creep, and hardness. So mostly all these terms can be obtained from the stress strain curve. The details about the stress strain curve and its components is followed in the part 2 video. Thank you.